So we're going to start chapter 5 in your textbook, and this chapter is on radicals. The first part is a review of grade 10, where we will define what a radical is. We'll take a look at what like and unlike radicals are, converting from a mixed radical to an entire radical and vice versa, and then the ordering of radicals. So that would be all a review from last year. The new stuff that we'll be looking at for this chapter will be adding and subtracting, multiplying and dividing, and solving radical equations. So let's start with our review. Radicals consist of a root symbol, an index, and a radicand. So here we have an example. Our root symbol is the bracket here. The index is the number that you will find in the little depression of your bracket here. So in this case it's n, so this is will be considered your root. And your radicand is whatever number is inside the square root bracket. And the whole thing is called a radical. It can be rational, for example, the square root of 4. All right, and the reason for that is that when you take the square root of 4, you get 2, and 2 is a rational number. Or irrational, for example, the square root of 2, and the reason for that is when we work out the square root of 2, on your calculator you would get 1.41 with a string of numbers after it. And you can see that this is non-repeating and non-terminating. Okay, and whenever you have a decimal that's non-repeating and non-terminating, it is irrational. Okay, and we're talking about a decimal here. If no index is specified, then the square root is meant. Okay, so all that means is if you have something like up here, this root 4, if we don't put a number in for the index, that just means we're looking for the square root. A radical always means to take the positive value. Okay, and I've got 3 scenarios here. We'll take a look at it. So, for example, both y equals 5 and y equals negative 5 satisfies y squared equals 25. Okay, and the reason for that is when I give you an equation like this where y squared equals 25, I'm not specifying whether your answer should be positive or negative, and so it's understood that when you take the square root of 25, it will be plus n minus 5. But if I give you the square root of 25, the answer has to be 5, and that's because your radical is understood to be positive, and so your answer will be positive. Okay, and we call that a positive square root. If you have the negative square root of 25, that would be the same as writing negative 1 times the square root of 25, which means you would have negative 1 times 5, which gives you negative 5. And so you can see that when you have a negative square root, your answer will be negative 5. Next, let's take a look at like radicals. Radicals that share the same radicand and index are called like radicals. When adding and subtracting radicals, only like radicals can be combined. That would be the same as if you were simplifying algebraic expressions, you could only add like terms. You may need to convert radicals to a different form, mixed or entire, before identifying like radicals. So let's take a look at this chart that I have here. In the first column you have pairs of like radicals, and in the second column you have pairs of unlike radicals. So let's take a look at the first row. In the first column we have 5 root 7 and negative root 7. So if you take a look, you have identical radicands. Okay? Note you do not have the same coefficients. That's okay. The other thing that's the same is both of these are understood to be square roots. Okay, so I'll just put a 2 here and a 2 here. So you can see that they share the same index. So these two radicals are like. They share the same radicand, they share the same index. It's okay that they don't share the same coefficient. Okay, in our next example, we once again have the same radicand, 5x squared and 5x squared. We have the same index. Notice it's a 3 in both cases. And again, our coefficients are not the same. You have 2 over 3 on the first one, and on the second one it is understood to be a 1. Now let's compare that to the next column. In the first row, we have 2 root 5 and 2 root 3. Now, notice that your radicands are different. Okay, they don't share the same radicand. One is 5, one is 3. Notice that they do share the same index. Okay, so they do have the same index. They're both 2's. And once again, in this case, we have the same coefficients. Okay, but we consider them not like, okay, even though they have the same coefficients, not that that would matter, and even though they have the same index, which would matter, they don't share the same radicand. And so these ones are not like because they don't share the same radicands. All right, and our next example, notice that we have the same radicands. They're both 5a, but this time we have different index numbers. One's a 4, one's a 5, and both coefficients are understood to be a 1, so they are the same, but once again, that wouldn't matter in this case. Okay, they are different or unlike radicals because they do not share the same index. Okay, so for these two examples, they don't share the same index. Now let's move on to restrictions on variables. Now this is really important when we're working with radicals. If a radical represents a real number and has an even index, the radicand must be non-negative. What that means is the radicand has to be positive or 0. Okay, it just cannot be a negative number. So the reason for that, let's take a look at the square root of negative 25. When we take the square root of negative 5, you will find that it cannot be negative 5 or it cannot be 5. And why? Because if I go negative 5 times negative 5, that gives me 25, which is not negative 25. Or if I go 5 times 5, that gives me 25, which once again is not negative 25. So this example here shows you that you cannot take the square root of a negative number. Even if I have another index which is something other than a 2, but still an even number, so let's say 4. So let's take a look at the fourth root of negative 16. The answer cannot be negative 2 or positive 2. And why? Because if I go negative 2 times negative 2 times negative 2 times negative 2, that gives me positive 16, which is not negative 16. Or if I go 2 times 2 times 2 times 2, that gives me 16, which once again is not negative 16. So you can see that if you have an even number index the radicand has to be a non-negative number. In other words, it must be positive or 0. Now let's compare that to odd-numbered exponents. So let's say you have the cube root of 8. Now if you take your calculator out, you will find that the answer for that is 2. And that's because 2 times 2 times 2 gives you positive 8. Now let's take a look at the cube root of negative 8. If you take your calculator out and you calculate that, you will get negative 2. And that's because negative 2 times negative 2 times negative 2 will give you negative 8. So you can see that if your index is an odd number, your radicand can be positive or negative because you will definitely get an answer for both of them. Okay? Alright, now that concept is very important when we're taking a look at what we call restrictions on variables. Let's take a look at an example where we have the square root of 4 minus x, and you can see that your index is a 2. Okay, so now we're dealing with an even numbered index. So that means that the 4 minus x, okay, which we're going to call our argument, okay, so the expression which is inside the bracket is called the argument. So the 4 minus x must be greater than or equal to 0. That means that it has to be positive or equal to 0. Okay, and how do we write greater than or equal to 0? We write it as greater than and equal to 0. So whatever 4 minus x is, it has to be greater than and equal to 0. So once you write it as an inequality like this, what you want to do is isolate the variable, and isolating the variable simply means, in this case, to solve for x. Okay? By applying algebraic operations to both sides of the inequality symbol. In other words, you just want to isolate. So if we want to isolate this, we need to add x to both sides. So on the left now we have 4 minus x plus x. Negative x plus x will give you 0, and you're left with 4, and 0 plus x is x. Now generally we do not write inequalities where the variable is after the inequality sign. We normally write it in front. So we're going to write that x is less than or equal to 4. And this is our restriction. So the radical, the square root of 4 minus x, is only defined as a real number if x is less than or equal to 4. You can check this by substituting values for x that are greater than 4, equal to 4, and less than 4. So let's try that out. Let's pick a value for x which is greater than 4. Okay? So let's pick x is equal to 5, let's say. Okay, so let's plug that in. We're going to go the square root of 4 minus 5, and then we get the square root of negative 1. So can we take the square root of negative 1? Well, try that out on your calculator, and you will find that you can't, right? And so this expression is undefined. Okay, so it looks like if x is a number which is greater than 4, we're going to get an expression which is undefined. So let's try equal to 4. So let's substitute in 4 for x, and we're going to get 4 minus 4, and 4 minus 4 is 0, and the square root of 0 is 0. And so it looks like if x is equal to 4, it works. Let's try a number where x is less than 4. So I'm going to plug in 3. Actually, let's plug in 0 because 0 is a nicer number. And we're going to get 4 minus 0. And 4 minus 0 is 4, and the square root of 4 is 2. And so it looks like we can definitely get the square root if we put a number in which is less than 4. Okay? So this restriction tells you that your number can be equal to 4 and can be less than 4. It just can't be greater than 4. So this concludes our introduction. In this first example for Chapter 5, we want to convert mixed radicals to entire radicals. And I just want to do a little review of what we mean by an entire radical and a mixed radical. An entire radical has a coefficient of 1. An example of this would be like the square root of 7. If I don't put a number in front of the square root bracket, it's understood to be a 1. Okay? And so we say it's entire. A mixed radical, on the other hand, has a coefficient which is other than 1. So an example would be like 2 root 5. Okay, so you have like a number in front of your radical sign, and this number would not be within the radical sign. So you have two parts, a number not inside a radical sign and a number inside the radical sign. So you have the radical and the non-radical. So you've been asked to express each mixed radical in entire radical form. Identify the values of the variable for which the radical represents a real number. So what they want you to do is to give any restrictions. On the variable. Now, if you recall from our previous discussion, the only time you have to worry about that is when your index is an even number. Now, on our first example, we don't have to worry about restrictions because we don't have any variables. And that would be the only time that you would have to worry about a restriction. So we want to write this as an entire radical. So I'm going to go through what you guys did in grade 10 last year, and then I'm just going to simplify things a little. We have an index which is a 2, and we want to rewrite this so that it's entire, meaning that we need to take our number which is outside the radical sign and we need to put it on the inside. And because our index is 2, that means we want to take the 7 and we want to square it. And so we're going to write the square root of 7 squared, and then we'll times it by the radical that we are given, which is root 2. Then we will simplify the first radical. We'll take the 7 square and we get root 49, and then we'll times that by root 2. And now we're going to combine them under the same radical sign, so we're going to get 49 times 2, which gives you the square root of 98. Okay, so what I want to do for this year is, instead of writing all these steps, I just want to combine everything within the same radical sign to start with. And so we're going to get 7 squared times 2. That gives us 49 times 2, which gives us the square root of 98. Okay, so you come up with the same answer in both cases. Okay, our next example does involve variables and an even index, which is understood to be a 2. So what we want to do is we want to take this a to the 4th and we want to put it inside our radical sign. And so we will write one sign, and I'm going to take the a to the 4 and I'm going to square it because my index is a 2, and then I will times it by the a that's already there. And when I square a to the 4, and if you remember, when you raise a power to a power, you're going to go 4 times 2, and so that gives me a to the 8 times the a that's already there, and I get a to the 9. Now, because we have an even numbered exponent, and we're dealing with a variable which is inside the radical sign, we have to worry about a restriction. And our restriction tells us that whatever the argument is, which in this case is a, it has to be greater than and equal to 0. And so our restriction is that our argument a must be greater than and equal to 0. Now, on the example that we did on the introduction, we had a binomial within the square root bracket, and we don't now, so we don't have to do any kind of simplifying. We can just leave it as a is greater than or equal to 0. And we do this because we have an even numbered exponent. Now, compare that to our next example where we have an index which is 3. Okay? That's an odd number, and because we have an odd numbered exponent, we have no restrictions. Okay, so we can start right away. Now, our index is a 3. That means that when I go to put the 5b inside the square root bracket, I have to cube it. Okay, so I'll do that over here. So that means I want to go 5b cubed. Okay, and then times the 3b squared that we already have inside the radical sign. Okay, so I want to simplify, so I need to cube my 5b. Now that means I want to go 5b times 5b times 5b, so I want to go 5 to the third power, which is 125. And then I want to cube my b, so b cubed times, and then I've got 3b squared. And now I finish simplifying. I go 125 times 3, and I get 375. And b cubed times b squared is b to the 5th, and this is your final answer as an entire radical. Okay, so that concludes example 1. So before we go on to example 2, let's take a look at what we mean by radicals in simplest form. A radical is in simplest form if the following are true. Number 1, the radicand does not contain a fraction or any factor which may be removed. So if you have a radicand that contains a fraction, this is not simplified. Okay, because by convention, we consider radicals simplified if the denominator does not have a radical, and this one does because I can split the square root of 2 over 3 up into the square root of 2 over the square root of 3, and then you can see you have a radical in denominator, so that's not simplified. So the radicand does not contain a fraction or any factor which may be removed. So here is an example of one that is simplified. The square root of 2 you cannot simplify any more than it already is. There's no factors of 2 that I can take the square root of. Okay, like I can't, the factors of 2 are 1 and 2. Well, I could take the 1 out, of course, but if I put a 1 in front, it's just understood to be root 2 anyway. So you can't take the square root of 2. Okay, the second condition, the denominator does not contain a radical. So an example of one that is simplified would be like the square root of 2 over 3. Notice the 3 is not in a radical sign, so it's not a radical. So compare that to the example I gave you up here, which is not simplified. This one is simplified. Okay, the denominator does not have a square root. Okay, so an example of a radical that is not simplified is the square root of 18. And that's because 18 has a square factor of 9, which we can remove. So the square root of 18 then is simplified to 3 root 2. They're equivalent. And how do we arrive at that? Okay, well, I'm going to show you two ways. The first way you would have done last year, I can write 18 as a perfect square times another factor. Now, the perfect square we're going to pick is 9, and the other factor will be 2 because 9 times 2 is 18. And I'm going to choose 9 because it is the largest perfect square number that fits into 18 evenly. Okay? And I can split this up and say root 9 times the square root of 2, and the square root of 9, of course, is 3 times the square root of 2. Now, I wouldn't expect you to write this middle step. You can go straight from the first step, the square root of 9 times 2 to 3 root 2, because you can mentally take the square root of 9 to give you 3, as long as you remember to remove it from the square root bracket, because when you square root a number, you need to pull it out of the radical sign, okay? Because it means you're square rooting it. And so you're going to get 3 root 2. So the second way that we can simplify root 18 is by prime factorizing the 18. And if you recall, prime factorizing means to write a number as a product of its primes. So for 18 we would get 2 times 3 times 3, and you can check that by multiplying it out. 2 times 3 is 6, times 3 is 18, so we've done that correctly. And now what we want to do, we want to take a look at our index and then group our prime factors into groups of 2 if we can. And we do have one group of 2 3's here. Okay, and if you recall, 3 times 3 is 9, and we can take the square root of 9 much the same way that we did over here. Okay, so if I want to simplify this, then what I want to do is I want to understand that 3 times 3 is 9 and the square root of 9 is 3, and then leave the 2 that's in the radical sign, the one that we haven't been able to pair up with another 2, leave it inside the radical sign, and then we can say that the square root of 18 is 3 root 2. Okay, so notice that both methods we arrive at the same answer. Okay, and now we will move on to example 2 on the next page. So in this next example, we're going to express entire radicals as mixed radicals. You're asked to convert each entire radical to a mixed radical in simplest form. So we're going to take a look at using two methods to do the first couple of examples, and then I'll just resort to one method for the next two. So on A, one method is the prime factorization method. Okay, so what you want to do is you want to take the 200 and you want to write it as a product of its primes. So I'll just work that out on the side here. I'm going to use an inverted division sign and divide the smallest prime number into 200, and the smallest prime number is 2, so 2 goes into 200 100 times. And then I'm going to do that again, and 2 goes into 150 times, and then I'll divide by 2 again, and it goes into 25 times, and now I need to divide by 5, okay, because I can no longer divide by 2. And so in my radical sign then I'm going to write 2 times 2 times 2 times 5 times 5. Now because my index is a 2, what I want to do is group my prime factors into groups of 2 if I can. And I notice that I have a group of 2 2's and a group of 2 5's. And just to get you to think about what that means, the first group of pairs is 2 times 2, which is 4. And the second group of two factors is 5 times 5, and that's 25. And because we're looking for the square root of this number, I can take the square root of 4, which is 2, and the square root of 25, which is 5, and I'm going to leave my remaining 2 inside the bracket, right, because I can't take the square root of 2. And then on the outside then I've got 2 times 5, which is 10, and then square root 2. Okay, and the second method is the greatest perfect square factor. Okay, and what you do with that is you want to rewrite the 200 as a product of a perfect square and a second factor which is not a perfect square. Okay, and the largest perfect square that fits into 200 is 100. And I times that by 2 because 100 times 2 gets me back to the 200. Okay, and now you can see that you've got a perfect square here of 100, and the square root of 100 is 10. And so you have an answer of 10 root 2. Okay, so once again, you are going to be leaving the 2 inside the bracket. Okay, so we're going to use both methods on my next question, B. Okay, so the first method, we want to prime factorize. And this time, notice that your index is a 4. Okay, now prime factorizing c to the 9th just means going c times c times c times c 9 times. So this time, instead of grouping in groups of 2 because your index is a 2, we now are going to group into groups of 4 because our index is 4. And you can see that we have two groups of four factors of c. And if you were to multiply those out again, you would have c to the 4 for each one of those, right? Okay. Now we want to take the fourth root of c to the 4, okay, and just like, and I'll just illustrate that up here, just like a square root undoes a square, so I'll use x squared to illustrate that. So the square root undoes a square, so the square root of x squared is x. The fourth root will undo an exponent of 4. Okay, so if I take the fourth root of c to the 4, that leaves me with c. Okay, so I'll use that principle here. The fourth root of c to the 4 is c. And the fourth root of c to the 4 again is c. So I'm going to go c times c on the outside of my radical sign. And once again, I'm left with a factor that I cannot take the fourth root of. And so you can see my answer is c times c, which is c squared, fourth root of c. Okay, and the second method is the greatest perfect square factor. So what I'm going to do with this is I need to think, you know, how many times does 4 fit into my exponent of 9 evenly? And it fits in evenly 2 times, okay? So you could write c to the 4 times c to the 4. There are your two groups of 4, and then times c. Or, if you understand, you could also write it this way. I would say to myself, okay, well, 4 goes into 9 evenly 2 times, so 2 times 4 is 8, so I could write c to the 8 times c. Okay? Both of these mean the same thing, it's just that the second way is a little more compact, right? And then I'd say, okay, well, the fourth root of c to the 8 would be c squared. Okay, and the way that I would work it out mentally in my head is I would say, well, 8 divided by 4 is 2, so I'm going to have an exponent of 2 on my c. And then I write fourth root of c, and you can see that we get back to the same answer that we did using the prime factorization method. Okay, now the other thing that we want to consider with this is our restriction. Because we have an even index, and we have a variable inside our radical sign, we need to worry about a restriction. So we want to know when c to the 9 is greater than and equal to 0. Okay, so one way to think about this is we want to isolate c, or we want to solve c, right? So I could take the 9th root of c to the 9 and the 9th root of 0, okay? And just like a square root undoes a square and a fourth root undoes an exponent of 4, the 9th root will undo an exponent of 9, and so the 9th root of c to the 9 is c. 9th root of 0 is just 0, so here is our restriction. So whatever c is, it has to be greater than and equal to 0. Okay, so for our next example, I am going to use the greatest perfect square factor method. I know that the largest square root that's going to fit into 48 is 16, and it fits into 48 3 times, so 16 times 3 will give me 48. And I'm also going to rewrite my y to the 5 in the same manner that I did on the second step on b. Okay, so my index is a 2. What I want to know is how many times does 2 go into 5 evenly, and it goes into 5 evenly 2 times, right? So I'm going to say, okay, well, 2 times 2 is 4, so I have a y to the 4, and then times y to the 1, right? Because y to the 4 times y to the 1 gives me y to the 5, and now I can take the square root. The square root of 16 is 4, And the square root of y to the 4, well, you work it out by going 4 divided by your index of 2, and that's 2, so you're going to write y squared. And what you have left inside your bracket is 3 and y to the 1, and so you're going to go square root 3y. And here is your answer for this. And once again, there's a restriction that we need to worry about because our index is even. And so whatever y to the 5 is, it has to be greater than and equal to 0. And so you're going to take the fifth root of y to the 5 and the fifth root of y to the 0, and you're going to write that y is greater than and equal to 0. And so there's your restriction for that. So I have one more example for number 2, and I chose this because the index is an odd number. And if you recall, when your index is an odd number, you don't have to worry about any restrictions on your variable. So there is no restriction on x. Okay, so I'm going to use prime factorization for this question. So I'll prime factorize the 96 over on the left here. So I'll start by dividing 2 into 96. And I get 48. And then I'll divide 2 in again, and I get 24. And then 2 again, and that gives me 12. And then 2 again, that gives me 6. And 2 again, that gives me 3. Okay, so I'm going to write that inside the radical sign. So I'm going to go 2 times 2 times 2 times 2 times 2 times 3. And then I'll just go x times x times x 6 times. Okay, so because my index is a 5, what I want to do is I want to group all of my factors into groups of 5 if I can. And so I have one group of 5 2's, and I have one group of 5 x's. And so when I take the fifth root of this group of 2's here, that will give me 2. And then I take the fifth root of this group of x's over here, and that gives me x. And so then I'm going to go the fifth root of, and what's left over inside our radical sign is a 3 and an x. So that leaves me with 3x inside, and so my answer is 2x, fifth root of 3x. So that concludes our example number 2. So in our next example, we're going to compare and order radicals. 5 bentwood boxes, each in the shape of a cube, have the following diagonal lengths in centimeters. So over here on the right, we have an image of a bentwood box. And as you can see, we have a diagonal that goes from one corner to the other corner. So it goes along here. Okay, so from the 5 bentwood boxes we have, the different diagonal lengths are 4 times 13 to the half power, 8 root 3, 14, square root of 202, and 10 root 2. You're being asked to order the diagonal lengths from the least to the greatest without using a calculator. So what we mean by least to greatest is ascending order. Okay, that means like if you were going to go up, it would mean like you were going up a staircase, right from the bottom to the top. And if you were descending, that would mean going from the greatest to the least. Now you're being asked to order these diagonal lengths without using a calculator. So what you're going to have to do then is to make sure that you write them all as entire radicals. Okay, so our first number is 4 times 13 to the 1/2 power. Now, if you remember from last year, when a number is raised to the 1/2 power, that means you're looking for the square root. So this really means 4 times the square root of 13. Okay, so we want to take this mixed radical and we want to write it as an entire radical. That means we want to take the 4 and we want to bring it inside the radical sign. And when we do that, remember, because our index is a 2, we want to square the 4. So 4 squared is 16. And put it inside the radical sign, and you're going to have 16 times 13, which is the square root of 208. Okay, our next number is 8 root 3. We want to bring the 8 to the inside of our radical sign. We know our index is a 2, so we're going to square our 8. So we're going to go 8 squared is 64, and we're going to times that by 3. And so the square root of 64 times 3 is the square root of 192. Our next number is 14, and we want to write that as a square root, so that means that we want to square the 14 when we put it inside the radical sign, and so the square root of 14 is the square root of, the square root of 14 squared is the square root of 196. Our next number is already in radical form as an entire radical, so we will leave that the way it is. And then our last number is 10 square root of 2. We want to bring the 10, pop it inside the square root bracket, so you want to square the 10. 10 squared is 100. And 100 times 2 is 200, so now you have the square root of 200. Okay, so we're ready to order our numbers. We want to go from the least to the greatest, so ascending order. So the smallest number that we have here, as you can see, is the square root of 192. Our second smallest number is the square root of 196. Our next number is the square root of 200. The next number is the square root of 202, and then our last one is the square root of 208. So when you write your number, you always write using the original numbers, so the ones that are up here. And so our smallest one is 8 root 3, so we write that first, and then we write that it is less than our next number, which is 14, which is less than our next number, 10 root 2, which is less than the square root of 202, and that is less than our last number, which is 4 times 13 to the 1/2 power. And so we are now finished. So in this next example, example 4, you are being asked to add and subtract radicals. Now, you didn't do this last year, except maybe if you were in honors. And so what you need to know in order to add and subtract radicals is that you can only add and subtract like radicals. And so let's review what a like radical is. So a like radical will share the same radicand, and it will share the same index. Okay, so both of those have to be the same in order for you to have a like radical and in order for you to combine them. So you've been asked to simplify radicals and combine like terms. So in order to determine whether you have the same radicand, you need to make sure that both of your radicals are in simplest form. It's easy enough to know if they have the same index, but not always easy enough to know if they have the same radicand. And so in our first example, it looks like we have to simplify root 50. So the largest perfect square that fits into 50 is 25. So I'm going to write root 50 as the square root of 25 times 2. And 3 root 2 is already as simplified as it can be, because you cannot simplify square root 2 any more than it is. And I can take the square root of 25, which is 5, and I can remove that from the radical sign. And so I have 5 square root 2 plus 3 square root 2. And now I can see that not only do both of my radicals share the same index of 2, they also share the same radicand, which is 2. So when you go to simplify this expression, you want to add your coefficients, okay, which are 5 and 3, and you want to leave your radicand the way it is. Okay, so 5 plus 3 is 8, and you write your answer as 8 root 2. Okay, now if this is confusing, just think about if you had, for example, 5x plus 3x. Okay, this is something you're very familiar with. All you're going to do is add your coefficients, which are 5 and 3, and you are going to leave your variable as is. So you're going to go 5 plus 3 is 8, leave your variable as x, your answer is 8x. Okay, so try to take what you know about combining like terms with combining like radicals. Okay, in our next example, we have, once again, radicals which are not simplified. That would be the negative root 27, the negative root 80, and the negative 2 root 12. Okay, all of them need simplifying. So on the first one, the negative square root of 27. 27 can be written as 9 times 3. 3 root 5 is already simplified. You cannot simplify the square root of 5 any more than it already is. And root 80 can be written as 16 times 5, right? 16 is your perfect square, 5 is your prime number, or your number which you cannot take the square root of. And then minus 2 times the square root of, and then 12 can be written as 4 times 3. Okay, on the first one then, the square root of 9 is 3. Pull that out. That means you have negative 3, and you're left with this square root of 3. Okay, so this 3 is that 3. Your 3 root 5 is already as is. Minus the square root of 16 is 4. And you are left with 4 root 5. And on the next one, this gets a little bit trickier. So I'm going to write it in as few steps as I can, so listen carefully. You're going to take the square root of 4, which is 2. It comes out. You need to multiply it by the coefficient in front of the bracket, right? You need to go 2 times 2 is 4, and then square root of 3. So I'll do that over here. Okay, you've got negative 2 root 4 times 3. I'm going to take the square root of 4, which is 2, remove it from the radical sign, and I'm going to times it by the 2 that is on the outside already. And that gives me negative 4 root 3. Okay, so you don't have to write this. You can do the mental math for that, and that would leave you with minus 4 root 3. Now, remember, you can only combine your like radicals. They have to share the same index and the same radicand. So we have indexes of 2 across the board, so that's the same all the way across, but we have different radicands. We have a root 3 and a root 3, so these terms are like. Okay, we have a root 5 and a root 5, so these terms are like. Those are the only ones that you can add. And remember, you can only add the coefficient and you leave the radical as is. So negative 3 minus 4 is negative 7 root 3. 3 minus 4 is negative 1, and then root 5. And so your final answer is negative 7 root 3 minus 1 root 5, or if you like, you don't have to put a 1 in front there, you can just write 7 root 3 minus root 5. Okay, our last example for example 4 is the square root of 4c minus 4 square root 9c. where c must be greater than and equal to 0. So that's your restriction. They're telling you already that c has to be a number which is 0 or greater than 0. Okay, almost everything is simplified. Not quite. Well, actually it's not, because the first term's not either, right? We've got a 4 here and we're looking at square roots. So let's simplify. The square root of 4 is 2. You cannot take the square root of c. Minus. Okay, so listen carefully. The square root of 9 is 3. We're going to take the 3 and times it by the 4, and 3 times 4 is 12. You cannot take the square root of c, so we leave that inside the bracket. Do we have like radicals? Yes, we do. We have indexes of 2 on both of them, and our radicand is a c on both of them. So remember, you only simplify by combining the coefficients. So 2 minus 12 is negative 10, and you leave your radical as is. And so your answer is negative 10 root c, where c is greater than or equal to 0. And that concludes example 4. So in this last example, you've been asked to apply the addition of radical expressions. Your question is that you have a square with an area 24 square units, and it's placed beside a square that has an area of 50 units. In simplest form, write a radical expression for the perimeter of the shape formed. Okay, so let's write what we know. We know that we have two squares that are side by side. The area of the first square, the smaller one, is 24, and the area of the larger one is 50. You also know that the formula for the area is the side, so which we'll call s, right? S squared. And because we've got two squares and we're given the area for both of them, we will most likely need to work with a formula on the area for both of them. Okay? And why do I want to know the formula for the area of a square? Well, because I am given the area and I need to come up with the perimeter. In order to get the perimeter, I need to know the side length of each square. Okay, and the only way that I can do that is to use my area formula. Okay, so on the small square, so this will be for the small square, my area is 24, so I'm going to replace the a in the formula with 24. So I have 24 equals s squared. Now, in order to solve for s squared, that means I need to take the square root of both sides. Okay, now generally I would go plus and minus the square root of 24 when I take the square root of it, but because I'm looking at a side length of a square, the measurements of length can only be positive, so s is equal to the positive square root of 24. Now this is not in simplest form. I need to write this as a simplified, as a mixed radical. So the largest perfect square that fits into 24 is 4. And so when I simplify this, the square root of 4 is 2, and I'm left with 2 root 6. Okay, larger square. Its area is 50, so I'm going to replace a with 50. Square root both sides. Once again, positive square root of 50, because I cannot have a negative length. I am going to simplify the square root of 50. The largest square that fits into 50 is 25. And so s is equal to 5 root 2. Okay, so that means that each side of the small square is 2 root 6. And each side of the large square is 5 root 2. And what we're missing then is the length of that little part right here. Okay, so how do we get that? Well, we know that the side length of the large square is 5 root 2. And the side length of the small square is 2 root 6. So what you want to do is to take the difference between those numbers, right? You want to go 5 root 2 minus 2 root 6. Okay, so now we have all our side lengths. Now we can work out the perimeter. Okay, so the perimeter is, now take a look, we have 3 sides that are 2 root 6. Okay, so I'm going to add those up. 2 root 6 plus 2 root 6 plus 2 root 6. And I've got 3 sides that are 5 root 2. And then my last side, which is 5 root 2 minus 2 root 6. Okay, so let's combine our like terms. Now they all are square roots, so our index is the same for all of them, but our radicands are not. We've got 6's, and we have 2's. Okay. So we're going to go 2 root 6 plus 2 root 6 plus 2 root 6 minus 2 root 6. So we're going to go 2 plus 2 plus 2, which is 6, minus 2, which is 4. So we have 4 root 6. And then we have 5 plus 5 plus 5, which is 15, plus 5, which is 20. And so the perimeter of the shape is 4 root 6 plus 20 root 2 units. Okay, I use the word units because I don't know what my dimensions are. I don't know if it's centimeters or millimeters or what, right? So I'm going to say units. And I put the 4 root 6 plus the 20 root 2 in a bracket to show that they are one individual number, really, because I can add them on the calculator and I will come up with one number. And so I need to indicate that by using brackets. Okay, so this ends our section 5.1.